All right, now it's time to really have some fun. Let's do some multi-step stoichiometry problems and continue where we left off with the last video. Example 1. Nitromethane is a fuel occasionally used in drag racers. It burns according to the following reaction. So here's the reaction. It's already balanced for you. And so you learned in the last video that these coefficients are absolutely critical as they are going to become the molar ratio in our stoichiometric computation. Okay, so part A. What is the volume of nitrogen gas produced at STP if 3,160 grams of nitromethane are burned? Okay, so we are going from here where we have 3,160 grams, and we are being asked about a product here. And specifically, we're being asked about question mark liters, STP, so we're going to use 22.4 in our dimensional analysis here. So this is a gram to liter problem. Let's go ahead and look at that. This is grams of one substance. We're going to use the molar mass to get moles of that substance. Then we're going to use the mole ratio using our coefficients from the balanced chemical reaction to convert into moles of the other substance. And lastly, we're asked for the volume of the nitrogen gas at STP. Okay? All right, so I want you, as I've said before, if you feel like you can go ahead and attempt this, then please hit the pause button before I go over the solution with you. Okay, so this is exactly what we laid out on the mole map, and I'll walk you through it. So we're given this bit of information. And so, again, if you feel better putting that over 1, please do so. So we know that grams are on top here, then the grams of the nitromethane must be below. That's the molar mass. Then we have our stoichiometric ratio or mole ratio. It's a 2 to 1. Where does that come from? One last time, because I've said that a lot between this podcast and the last podcast, but it comes from those coefficients, and the chemical reaction has to be balanced correctly. And then we have moles of nitrogen gas here in the numerator, and so we need it in the denominator there. So everything factors out, and we're left with liters of nitrogen gas, which is what the problem is asking for. So you're going to multiply everything on top, divide by everything on bottom, and you will get an answer of 579.8165. Okay? Now, as far as sig figs go, this trailing 0 is considered insignificant. So we have 3 sig figs we need to deal with here, and plus 3 sig figs with the STP value anyways. So that number that you have is rounded, and it is rounded to 580 liters. And to denote 3 sig figs, you're going to need to use scientific notation, which is why I've written it as 5.80 times 10 to the 2, because any trailing zeros in a number that contains a decimal are considered significant. And once again, guys, significant figures are all based on actual experimentation and measured values. So just pay attention to sig figs is all I'm asking, and I'm trying to go through and reinforce that in this problem. So, all right, part B. What is the mass of nitromethane burned if, okay, so we have 955 grams, and we're being asked to go here. Remember, you can go anywhere. Question mark mass. How many grams of nitromethane if 955 grams of the nitrogen gas are produced. So we're going from a gram to gram. All right, let's take a look at that here. We're going grams. We're going to use molar mass. That's going to get us moles. We're not done. We're doing stoichiometry. I need the mole ratio from the balanced chemical equation. And then we're going to get moles of our other substance. In this case, it's the moles of the nitromethane, because we're going from the nitrogen gas to the nitromethane. And we're asked how many grams of that will be produced. Okay, so there we go. All right, so what I've just went through on the mole map, we're now going to look at that. We're going to convert the 955 grams of the nitrogen gas using the molar ratio, using the molar mass of both substances, making sure everything factors out. Moles on top, moles on bottom, 4 to 2 stoichiometric ratio, moles of nitromethane, moles of nitromethane. What are we in with? Grams. Is that what we're trying to go for? It sure is. What mass? That's what we're trying to get. Question mark mass. All right. And for this problem here, when you put everything, multiply everything on top, divide everything on the bottom, what you're going to end up with here is 416.0.827. We're going to need 3 sig figs in this problem here. So, you know, yes, that would round up, but we are reporting this with 4.16 and times 10 to the 3, because that's going to give us this value here. Now you could also report this, because that's technically 3 sig figs as well, with that trailing 0 and no decimal. Either one of those is perfectly acceptable for me. All right, so what mass of water vapor is produced in the exhaust along with 3.5 times 10 to the 25th molecules of nitrogen gas? Okay, molecules, those are chemical units. You should be thinking right now, Lorenzo, Romano, Amadeo, Carlo, Avogadro. You're going to use Avogadro's number in this computation here. Okay, so we are going water to nitrogen. Okay, so water and nitrogen. So that's pretty cool. So we're going within the products here, and we're trying to ultimately find out how many grams of water. Okay, so let's go ahead and look at our mole map here. And we are going from particles or chemical units of A. We're going to use Avogadro's number. Okay, that's going to give us moles of A. Then we're going to use the mole ratio from the balanced chemical reaction to get moles here. Then we're going to use the molar mass to finally get the grams of water for this problem. Okay? All right, so give it a shot on your own, and I'm going to go over the solution right now. So we are converting our molecules of, there's Avogadro's number, and that number is the number of chemical units in 1 mole. Then we're going to go ahead and look at moles. We have our stoichiometric or mole ratio going on right here. It is a 6 to 2 ratio, and moles of nitrogen gas cancel out. Moles of water, in 1 mole of water, there's 18.02 grams, so that cancels out. We're left with mass. Multiply everything on top, divide by everything on bottom. Paying attention to sig figs, I'm going to need 2 sig figs. And so for this example here, let me write down what you'll get. You'll get 3141.979. Okay. That's what your calculator will spit out at you. And then paying attention to sig figs, we are able to adjust that and report it as basically 3100, 3100, or using scientific notation 3.1 times 10 to the third. I like that approach better, but in the end, that's going to be up to you guys on how you proceed. Before we move on, I do want to mention something here. Back in part B, we have our nitrogen gas. It's the nitrogen gas, all right? The diatomic form. That's why this number is not 14.01. It's 28.02. So just be aware of that, because that's going to throw off the entire problem. Now, if you want in class, I'll probably show you, if you want to use nitrogen gas, you would use the composition stoichiometry by saying in every 1 mole of nitrogen gas, there are 2 moles of nitrogen, multiplying by 2 to get 28.02. They both work. They'll do the same thing. All right, so let's go ahead and move on to our next example here. Here we have aluminum reacting with chlorine gas to form aluminum chloride. And we're asked what mass of chlorine in the presence of excess aluminum, so there's lots of aluminum, is required to make, I see kilograms, I know I'm either going to be multiplying, or somehow I'm going to factor in that there are 1,000 grams in 1 kilogram. So bump the decimal 3 to the right. However you want to do it, just be aware of that. That should stand out at this point. Okay, so go ahead and get your balanced chemical reaction, because you're not doing stoichiometry unless you have that, because we need that mole ratio. And here it is. We see we have a 2 to 3 to 2 stoichiometric ratio in our balanced chemical equation. And we are right here. We have aluminum chloride 4,560 grams. And we're being asked what mass of chlorine? Question mark, grams in the presence of excess. Okay, so getting the lay of the land here. We are going from grams of one substance. We're going to use molar mass, of course, to get us to moles of one substance. And then we're going to use our molar ratio here to get us to moles of the other substance, and ultimately end with molar mass of that substance B to get grams of substance B. Okay? All right. So I'm going to go ahead and lay out what we just discussed on the mole map, starting with our value. Now, in this case here, I'm showing you, it really doesn't matter, but in this case, I've started with my kilograms, and I'm using dimensional analysis to factor that out. Then we're moving into the molar mass of this substance, which gets me to moles of aluminum chloride. And now I want to get something, I want to convert to moles of the chlorine gas. How do I do that? The mole ratio, it's a 3 to 2 in this instance. And then once you get that, now we're dealing with chlorine gas. So in 1 mole of chlorine gas, there are, now don't forget to multiply by 2, because we're keeping it in its diatomic form. Okay, so 35.45 times 2 is what's going to give you your accurate molar mass for chlorine gas. We're going to pay attention to sig figs. We're going to acknowledge that we need 3. And so in this case here, we can report this. You could also do 3640. That has 3 sig figs. Either one of those would be acceptable to me. Okay, example 3. Carbon dioxide gas is produced in the reaction between calcium carbonate and hydrochloric acid. If 15 grams of calcium carbonate reacted with an excess of hydrochloric acid, how many grams of the carbon dioxide? So I'm going to say we want to go grams, and we start with grams of the reactant. We want to know about the product. Now, before you pause and you get started, I want to give you a little bit of direction on this one. Remember, you're going to form what looks like carbonic acid, and that's going to spontaneously decompose into carbon dioxide and water. Now, we've talked about this several examples when we talked about oxidation reduction reactions, when we talked about metathesis reactions, compare and contrast in chemical reactions, podcast 5. Example number 5 was the first time I really went through this and we talked about it. And there's other examples. Ammonium hydroxide will spontaneously decompose into gaseous ammonia and water. All right, so heads up on that. When you get the carbonic acid, you're going to have to break that down into water and carbon dioxide. And you will get the following balanced chemical reaction here. So now we can figure out what's going on here by putting our 15 grams here. And we want to know how many grams of carbon dioxide would be produced. This is a gram to gram problem. If I pull up our mole map here, we'll see going, oops, not there. We're going grams, molar mass, moles, mole ratio, moles of B, and then molar mass once again, because it's a gram to gram. Okay? All right, so moving on. And I'm going to lay this out, starting with our value that we're given that has 3 significant figures of 15.0 grams of calcium carbonate. Using molar mass, factor out, that gets me to mole. It's a 1-to-1 mole ratio. Now, if you want to just look at it later on in the course and say it's a 1-to-1 ratio. For every 1 mole of this, I produce 1 mole of that. That's perfectly fine. But for now, keep it in your dimensional analysis, please. 1 mole calcium chloride. Now I'm dealing with moles of carbon dioxide gas. And in 1 mole of carbon dioxide gas, there are 44.01 grams of carbon dioxide. And what am I ending with grams? What is it asking me for grams? I'm double checking. I'm thinking out loud. I'm modeling the process with you. Multiply everything on top, divide by everything on the bottom, and you will get 6.60 with 3 sig figs. Okay? Now, let's see here. 6.5955. So your calculator spits out this answer, and the question is right in here. So here's our 5. Now, we want to make this last digit, the one that is not dropped, we want it to be even. Okay? 0 is considered even in the mathematics. So this number here rounds to 6.60 grams of carbon dioxide. All right? Okay. So example number 4, lots of practice here before we move on to other concepts in stoichiometry. What mass of water vapor would be formed? Okay, so mass of water vapor would be formed from the complete combustion. So that's one way of saying that all of the hydrocarbon, all of the combustible compound is combusted. In other words, the reaction goes to completion, all right? Which is an assumption that we're going to really dial in on an upcoming podcast. But for now, I just want you to think of that. And we're starting with that many grams of the ethanol. Okay, so go ahead and get your combustion reaction, get it all figured out, go through, balance it. You'll end with a 1 to 3 to 2 to 3 ratio. In this case here, remember, it is combustion, so we're assuming at a high temperature. All right, so our water here is water vapor, and it's gaseous in this case here. All right, and that's a minor detail, but I want to, again, we're going to start looping and reinforcing ideas as we get, further into the course content. Okay, so I have 35.00. And I want to know question mark grams. So I'm going from one reactant to a product in a gram to gram conversion. All right. So in my mole map here, oops, there we go. In my mole map here, gram to gram, molar mass, grams of A. What would A be in this case? A is our ethanol. We're converting, we want moles of ethanol. Then we're going to use the Stoich ratio and convert that into moles of water. Once we get moles of water, we're going to use the molar mass of water to answer this question about how many, what mass of water vapor. All right, so let's get this going and finish this one up here. 35, you want to put it over 1. That looks horrible. You want to put this over 1, that's fine. Boom, boom. Factoring out 3 to 1, 3 to 1. I'll put the 1 there. Now we're in moles of water. In 1 mole of water, there are 18.02 grams of water. And that's going to give you, with 4 significant figures, 41.07 grams of water on this problem. All right, so we made it through. You've had lots of practice. You're going to get even more practice when you start working on the problem set corresponding with this podcast. You're going to get lots of practice applying those computational skills with stoichiometry. We're also going to have a number of labs coming up where you're designing and carrying out experiments and investigations. So we're just getting started. This is one of my favorite units, guys, and I'll see you in class.